In this section of Chapter 5, we're going to talk about the physical and chemical properties associated with the isomers. So what we're going to see is that constitutional isomers have different physical and chemical properties. Remember, constitutional isomers are the ones that have different connectivity. So we arrange the atoms in a different pattern. So they're going to have different physical and chemical properties because the bonds are arranged in a very different pattern. So then we just talked about enantiomers. Remember, enantiomers are those non-superimposable mirror images. So the only thing that changes is their three-dimensionality in space. And what we're going to see with enantiomers, their physical and chemical properties are going to depend on the chirality of the environment that it is in. So an achiral environment is typical lab settings where it's a beaker, it's water, it's a solvent of cyclohexane. They're very achiral environments. And what we're going to see is that in this achiral environment, our enantiomers have the same physical and chemical properties. It doesn't matter that the chlorine's pointing out or pointing back. It has the same polarity, it's going to show the same properties, it's going to have the same boiling points. So in an achiral environment, they have the same physical and chemical properties. But if we can put the enantiomers in a chiral environment, meaning that there's some chirality associated with it. This type of environment is typically going to be like your body. We've got a lot of molecules in your body, and they're in a chiral environment because they're interacting with proteins, and proteins have a lot of chirality associated with them. They're interacting with enzymes, and enzymes have chirality associated with them. So if we can somehow put them in this type of chiral environment, to manipulate that or to simulate that in a lab, we would need to make sure that whatever solvents we're using are chiral in nature as well. So if we can do that, then our enantiomers will have some different physical and chemical properties in relationship to whatever has been manipulated for the chiral environment itself. So it's not very easy to make these chiral environments in a lab. So it is very, very difficult to have or to let the enantiomers show different physical and chemical properties in a lab-based setting because we're in that achiral environment typically in our lab. Diastereomers are going to have different physical and chemical properties. So remember, diastereomers are different in one chiral center where one chiral center stayed the same. If we've got two, if we've got more than two, one changes and the rest are left the same. Because of that, they are going to show some different physical and chemical properties when we start looking at diastereomers, regardless of the type of environment that we are in. So one of the things that we oftentimes have to worry about with our isomers is basically separating them. Because if we typically run a reaction, we can oftentimes create more than one of those isomers in solution. So we have to be able to make sure how are we going to separate them. So diastereomers are going to be very easy to separate, and we can separate them under typical lab separation techniques that we have been working on in the lab. Distillation, crystallization, differencing in solubilities. Because remember, their physical and chemical properties are very different, and we can take advantage of those differences in order to separate them out if we generate diastereomers in our reactions. But if we create enantiomers in our reaction, they're going to be very difficult to separate because remember, they're going to have the same physical and chemical properties under lab-based achiral conditions. So in order to separate them, we would have to generate chiral environments. We would have to somehow interact them with other chiral compounds in order to separate those two enantiomers from each other. Another option that we have with our enantiomers is that we could separate them by running different reactions. We can convert them into diastereomers, so run a chemical reaction. Then we can separate those diastereomers and then run another chemical reaction to convert those enantiomers back to what they originally were. So there's a lot more reaction here. And remember, every time we run a reaction, we lose more of our compound. So our percent yield would go down just because of this separation, because we're running two new reactions in our process to actually let the separation happen as well. This is one of the reasons why pharmaceuticals become so expensive for us. Most molecules that are pharmaceuticals are chiral in nature, which means they have enantiomers. And oftentimes what we will see is one enantiomer is effective as a pharmaceutical, and under the best conditions, the other enantiomer is not effective. but would still mean under my reaction I would generate both of them in my reaction flask. And if I'm generating 100 grams and it's 2 enantiomers, potentially only 50 of those grams would work as a drug. So then only half my drug is effective. So which is why we typically find ways to separate them so that things are pure. We don't contain all this extra stuff. And that's just if the enantiomer is non-effective. Oftentimes what we see with pharmaceuticals is that one enantiomer is effective, but oftentimes the other enantiomer is toxic. So now if I have both of them in my pill, I can't give it to you. Half of it's going to help you, but then half of it's going to hurt you. So then we have to find ways to separate them. And that separation is not always easy, which is why it takes so long to produce pharmaceuticals. We go to so much work because oftentimes with this enantiomeric process, it becomes very difficult to isolate the compounds that we actually need. But one of the things that is going to be different about enantiomers and how we can judge whether or not we have enantiomers is going to be through optical activity. This is one of the things that does allow us to determine if we have enantiomers and what type of enantiomers we have. So ordinary light has waves, and those waves oscillate in an infinite number of planes. So if we really think about this, one of the ways that we will oftentimes draw this is going to be that we have our light, and I'm just going to denote it here in a circle like we're looking through an eyeglass, and it oscillates in tons and tons of different waves and different patterns. So if we take this normal light and we pass it through a polarizer, what that does for us is now we're only going to get one plane of oscillation. This is what we refer to as plane polarized light. So I'm going to pass my light through a polarizer. Sometimes polarizers, you can kind of think about these as your sunglasses as well. Sunglasses are often polarizers. They get rid of certain wavelengths that we have. It's the same type of process, but we would do it to a very specific extent so that we only get one plane of oscillation when we look at our light. And we have equipment in the lab that would do this for us so that we only have one plane of oscillation of our light. What we're going to see with this plane polarized light is that if we pass that through a chiral compound, that light rotates. And this is what we refer to as optical activity. It's the rotation of plane polarized light when it is passed through a chiral compound. So if I take this plane polarized light and I look at it under the context of a molecule, what I am going to see is that that light is no longer going to stay in this position. So when we pass the plane polarized light through our molecule, instead of that plane being straight up and down, we're going to see a rotation in that light. That rotation can either be clockwise, that we see here. This is oftentimes going to be denoted by a plus sign. And this would be considered a plus rotation. Your textbook walks you through how to calculate this amount of rotation, which is denoted by the symbol of alpha. You do not need to be able to do those calculations for me. We're going to look at this once again from a very qualitative perspective in terms of the directionality and the notations and the terminology with it. We will not do any of the actual calculations for amounts. But with this positive alpha that we have, this rotation clockwise, this would be considered a dextrorotatory directionality for our rotation of our plane polarized light. So if you think about this in terms of the biology that you have probably seen, you've seen D and L in front of oftentimes our molecules. It's because those are going to be enantiomers, specific enantiomers. The D and L would represent which direction that molecule would rotate plane polarized light. So that dextrorotatory would be in that clockwise direction. It would have a positive alpha associated with it. The other direction that we could see with this is going to be the counterclockwise direction. So this would have a negative alpha associated with it. And this would be our levorotatory directionality that we would be looking at. So what we're going to see is that one of the enantiomers will rotate clockwise, one of the enantiomers would rotate counterclockwise. So with this, the extent of the rotation that we see, so that would be the amount of that alpha change, is going to be dependent on the amount of active molecule that we have And it's going to be dependent upon the length of the tube, so how much light is going to shine through the sample that we have. So based on all that information, we can use optical activity to determine how much of the molecule we have, or the concentration of the molecule, if we're dealing with a solution. We can only determine the rotational direction based on experimentation, not the type of chiral center that we have. Meaning I can't pre-predict which direction an enantiomer is going to rotate the light just based on the structure itself. I would have to actually run the experiment to determine if it rotates the plane to the right or to the left, clockwise or counterclockwise. I cannot predetermine that without the experimentation, which is why everything gets labeled with those D's and those L's, or those pluses and those minuses, so now we know which directionality it actually rotates. Once we know that information, we have that relationship, we can use those D's and L's, or pluses and minuses, to tell us about the chiral center that we're dealing with. One of the problems that this does express for us, though, with optical activity is if we have racemic mixtures, meaning if I have a mixture that is an equal mixture of both enantiomers, so a nice 50-50 mixture, equal mixture, it's equal amounts, we have a racemic mixture, we will not see any optical activity. Because we have equal amounts of what would rotate clockwise and what would rotate counterclockwise, we don't see any rotation. So that is one of the downfalls to optical activity, is that most of the time when we run our reactions in normal lab environments, we get these racemic mixtures. So then if I run optical activity, I would not see any plane polarized light. So then it would tell me, if I was making enantiomers and I knew I was going to make enantiomers, that I made a mixture of both of them, and it was equal amounts of both of them. If I wasn't sure if I was going to get an enantiomer, get any stereocenters, this would not help me. I wouldn't know, since there would be no plane polarized light. One of the good things about this, though, is if I do have unequal mixtures of those enantiomers, we will see the light rotate based on the excess enantiomer that we have. And this is what we would refer to as an enantiomeric excess, or EE. So if you're reading any articles and it talks about an enantiomeric excess, or EE, basically it's telling you how much excess you have of one of the enantiomers over the other, based on how much light was rotated under our optical activity.